Hello everyone, I'm Wang. I'm a PhD student working at Purdue University on the 3D printing concrete project with Dr. Oleg, Dr. Cementitious, and Dr. Youngblood. And today I'm going to talk about our recent work on the cellulose nanofiber. So we are also trying to study the rheology, compressive strength, and a little bit of cement hydration on that. So I'm going to start with this slide. So the rheology for the cement or concrete is actually back starting the self-compacting concrete. So for the self-compacting concrete, like you see in this figure, we need kind of low yield stress to let the concrete pass through this reinforced structure. And in the meantime, we need relative high viscosity to prevent segregation, prevent bleeding, right? So, however, for 3D printing concrete, we need a totally different behavior. Because for 3D printing concrete, we are doing it layer by layer by layer. So we are keep imposing stress to the bottom layer of the concrete. So we need relative high static yield stress to prevent the yielding failure as we build. And in the meantime, because of most of the 3D printing concrete process, we have a extruding or pumping process. We need relative low viscosity to reduce the pumping pressure to increase the flowability. So to achieve this, a lot of research is done by increasing the binder volume fraction. We need to achieve these rheology properties. And also because the limitation of the core segregate, we also need a large volume of the binder. So besides the binder, we also need a lot of additives. We always use a lot of additives, such as the viscosity modifier, it can reduce the bleeding and increase the ink consistency. Or sometimes we use water reducer to increase the flowability, or accelerator to increase the hydration rate to make it harder faster. Or they come to the topic of this section is the nanomaterial. It also have a lot of benefit. So it has rheology, mechanical performance, or durability performance. So all these additives we can choose, but it kind of increase the complexity of our mix design. And also, they are not cheap. Most of them are kind of expensive compared to other material we are using. So this comes to the two objectives we are trying to study. The first one is we are looking for cost-effective additives. And second one is because of large binder volume fraction we are using, we are also trying to increase the graininess of our binder. So the potential additives or the mixtures we are trying to study is, again, similar topics, cellulose nanofiber. So it's come from the wood or trees. If we scale the tree from meter scale to all the way to the nano scale, there are actually two materials we can get. One is CNC, it's cellulose nanocrystal. It's like this crystal-sized structure. And CNF is cellulose nanofiber. It's a fiber structure nanomaterial. And cellulose is widely used. Not widely used, it's widely available. So we use wood product every day. So we produce 1.5 billion cellulose per year around the world. Billion tons, sorry. And again, the cellulose nanofiber, the information I got is $75 per pound per dry weight material. That's why I was asking $1 per pound, a little bit confused. So I bought that from the Humane. So they are internal price. All right. So let's continue our material and method. So we are trying to study, again, the rheology and mechanical properties and hydration, a little bit of hydration. So we use start with small content, small dosage, start with 0%, 0.15, and 0.3. So these are calculated with respect to the dry weight of the total binder. And again, our CNF is pretty much the same as what Dr. is using. 3% solid volume fraction, and 97% water. And again, same figure from UMain datasheet, so fiber structure nanomaterials. And besides CNF, we are also trying to study if we replace limestone failure, how it will affect the rheology on 3D printing concrete. I know especially a lot of state is switching type 1 to type 1L, so which limits the limestone content to 15%. However, as we just recently read that in Europe, there's a EN 197, they kind of limit the limestone content to 35%. So we are also interested, okay, so if you increase the limestone failure content, how much you affect the rheologically or mechanically? Especially at this point, for 3D printing concrete, a lot of the applications are like one-story building, two-story building. We actually don't need that. I mean, for certain applications, we don't need that super high performance. So which means if we can maintain the overall mechanical and durability performance, we could like reduce the amount of cement we are using. So let's come to the next slide. This is our rheology prototype. So we start is the pre-shear to make sure all the material is in the same static state before we test, and then we induce a shear ramp. And after that, we apply a small amplitude acceleratory sweep to test the storage modulus. So let's look at some of the rheology results. So the first parameter we are trying to measure is the static yield stress, which is really important for 3D printing concrete. So the result they show is like by only 0.3 CNF, we can increase the static yield stress by like 8 times, by only 0.3 CNF. So I know a lot of studies talking about nanoclay is also, like, we have results from one of our colleagues. And nanoclay, if we normalize the percentage by 1% by weight, just for comparison reason. So CNF can actually bring 10 times more static yield stress compared to nanoclay. And the second parameter we are trying to look at is the dynamic viscosity. The dynamic viscosity is really related to the pumping pressure. And so as you can see, if we increase the CNF content, we also got an increase in dynamic yield stress, which implies that we will have a high pumping pressure. So partially due to the nanoscale like colloidal interaction between the CNF and cement to the viscosity to bring up. However, it's interesting if we add more replacement on the limestone failure, we got a like the effect of the CNF on the dynamic viscosity got minimized. So which means we can get like relative low pumping pressure by combining the CNF and limestone failure. So the other parameter we are looking at is the storage modulus, which is, you can see that the storage modulus is for like type 1L is compare type 1L cement and the 40% replacement of limestone, we can see a high increasement on static yield stress. But on the other hand, if we only look at CNF, it doesn't like affect any storage modulus, like not that much, a little bit, but not really significantly. So all of these are rheology parameters. So how the printing will look like after we like test all these like rheology parameters. So we design a structure with like really large overhang, because in order to print this, of course you need really high or good rheology properties, high static yield stress, high stiffness, and high critical strain. So we scale the mixture to mortar, which we have assigned to binder content of 1. And if we look at the first one, we look at only the cement, water, and sand, without any additives, without any CNF. We can see that it cannot print. It cannot have any buildability. It will just fail as it print. So if we look at the one with only replacement of limestone, so we can see that because of a little bit improvement on the static yield stress and some improvement on the storage modulus, it can build until 12 layers, but it's just buckling failure. So after that. And if we look at the mixture with only 0.3 CNF, we can see that the first I want to mention is only 0.3 CNF. The dynamic viscosity got like shoot up. So in this case, because of the equipment we are using a syringe to print the mixture. We don't have a shear like mixing in our extruder. So it's a static extrusion. So I really have issue to extrude the problem because of the increasement of the dynamic yield stress. So dynamic viscosity, sorry. So I have to like add some water reducer to increase the flowability because of the equipment. And then, again, it's not really comparable because I have to add water reducer, but it still can print, I guess, up to like 12 layers. But it not fail immediately because we still not reach the static yield yet. So after like 25 layers, it failed completely. And so you can see none of that work. So what about if we add both CNF and limestone together? So first, we can bring the dynamic viscosity down, so I don't have any problem with the extrusion. So we shoot up the static yield stress and also the storage modulus. So we finally got a successful print, can handle really, the mixture can handle really large overhang, and more importantly, we are only use CNF, which is cheap and natural material, and limestone failure, also considered cost effectively. So you may be interested, we got a mixture can print, but what is the mechanical property? That's also important. So we did test the 28-day compressive strength. First, you can see that, of course, by replacement limestone, you will see a decrease in the compressive strength by the dilution effect. But another effect we noticed is by adding CNF, it can also have a trend by increasing the compressive strength to offset that phenomenon to some extent. So at least, especially for when we have sand enough binder, we have sand to binder ratio of 1. So it's also most of the mixture, the compressive 28 compressive strength is larger than 35 megapascal, which is kind of meets the overall performance requirement for the general low-story building, at least for a lot of application for the 3D printing concrete. We do some calculation, make another plot with the cement volume fraction and compressive stress per cement content, which is normalize the compressive strength with the cement content. So we can see that there is a trend, that clear trend, if we plot all the data points together. There is an increasement. As we decrease the cement volume fraction, we also got more efficiency on the normalized compressive strength per cement volume fraction. So we then went ahead to run some isothermal calorimetry. There are a lot of curves, a lot of groups in there. So if we only look at the initial stage of the isothermal calorimetry and look at if we only separate CNF curve, we can see that it doesn't, it has some acceleration effect, but not really significantly. So most likely the improvement on the mechanical property are due to the physical effect, which is fiber structure material. So it can kind of first bridge the macro crack. Second, it can have interaction between cement particles, so it could improve the strength. And if we only look at the limestone failure, so it's similar like we see in the literature. So we replace cement with limestone failure because of nuclearization effect, and also because the more effective water cement ratio, we got if we normalize the heat by per gram of cement, we got a significant acceleration effect on this mixture. And this is also agrees with the storage modulus, because the increasement of storage modulus is partially due to this acceleration effect. Because more hydrogen accelerate, you got increasement on the storage modulus. And yeah, so this is more some of the result. And the conclusion, again, additional CNF can significantly improve the rheology properties that good for 3D printing, like static yield stress. And also, if we replacement cement with limestone failure, we can increase both static yield stress a little bit, and also storage modulus or stiffness, which can prevent the buckling failure. And if we combine them together, we can have a really highly printable mixture and also highly cost-effective mixture. In the meantime, we can maintain the overall mechanical performance to 35 megapascal. So the future work remain in the durability properties, because by replacement the cement with limestone failure, we are interested in durability properties. However, there are already few studies shows CNF fiber, a small amount of CNF fiber can improve the durability performance significantly. So it can also offset some of the dilution effect to some extent. And also we'll study what the real mechanism between the interaction of the CNF and cement and limestone. So, and this is my reference. And thanks for the professors for the help and support. Also thanks for my college and team member, Dr. Aladoba. And I'm happy to take questions.